You just got there. Oh yeah. Then it was back there. Man, you're just across the country. You use that I had. That I had. Over there.
Like it says recording, but I don't know what it's recording.
Right.
And then.
Well, he's Josh Joy.
Josh,
What's up?
you wanna drop it in the Slack and I'll just sign on to see what you're doing, or you have.
Michaela has it on her laptop, but what I'm having a problem with is that it seems like it only wants to record from my computer because I created the call, which it's fine.
Not with cross guys, but with systems.
Where are you guys staying?
Yeah.
Were you staying like Airbnb or you self chat? My wife's family lives
To the house, basically.
so we swear you. It was just like halfway to the act, and then. Right, so
Yes.
yeah, well, very rural.
It's
Just we don't want this nice sort of. Yeah, went out. Cricket chairs, yeah. Oh, no. Cherries are. They're good.
The experiment where you. Low bank.
And we got a farm today, so we would love to have. Smells like. Area, and then people figure out after here, 30 years and kills all the time. Yeah, I thought it happened last week, the Washington crew did something that.
So the banks Washington, no experiment besides just one, but. So you guys do that, but you climb some peaks.
Because the least is playing Washington. We try to take part of the. Easy route, South really would expire.
My guess is.
That might be the.
What's it?
So they can hear you.
That's good.
Yep.
Good time. Yeah, except then I think.
And you could come to
My son has been fighting us for the fraction. They do antibiotics and like you can't act. I wound up like carrying him.
Do you want me to go try to put the food in the other room?
If you want to.
like a carryable size.
Not really, I had he's 50. I don't know. For the average human or for. I had to drop it like I was gonna carry him down to the car and then he's going back up to the backpack, but he's. Great, that carrying.
Actually,
with her.
I didn't know that about the others with this on.
So.
There is a Zoom option, I think you put a Zoom option on that.
I did put a Zoom option. Does somebody need it?
We don't know where Mike and.
Are you texting them? Yeah.
Not sure where Mike and Sean are.
We had 5 days, no look at national park. Nobody's. Tried to rope the kids up on Olympus.
So I'll go run through the bathroom real quick then while they're.
Yeah.
Oh.
Don't enjoy it too much. It's gonna be fun until it isn't. It was a little bit concerningly unconcerned. They're showing some pictures of people stuck in the. Yeah, well, he's been keeping really. Yeah. And it's, you know, the instructions look for adults, but it's got super fun pictures. And we can. Give it a so he was super excited to see little holes in a glacier, so he wanted water and so on. But we found a few small ones. Yeah, super excited to like. Look in the hole. The ice water poured out. Where you went? Yeah, one. He's lowering down and you were lost. It's one of the coolest things I've ever done. Yeah, never had a climbing out like ice axes instead of ice tools. Not as much fun. Very challenging. Yeah. It was and that ice is hard, but it's yes. Really. I was like on the corner by which place like that's engineering. I don't know. I don't. But we got there. We got like 2/3 of the way up, maybe 600 feet on the mountain.
And for a uniform, figure out like how fast is to jump into it. And like running first. That's too large. Okay, let's just go right across the we think it's got similar songs. Oh,
I just checked. I have an email from Mike. He's gonna join virtually.
Yeah.
So I'm gonna send him the link. Yeah, that's fine. I'll just have to screen share.
I would put it in the chat.
You probably still see carriers. Yeah, so probably. I think what you would probably see is you'd see a rapid switch. Yeah. I know nothing. Well, now that we got this. Yeah, or, you know, Okay.
I'm sorry, Josh, we're talking about beyond the back.
It's okay.
Just right there, yeah.
Josh, I feel okay. Okay. Mike, you're here. Can you hear us?
Yep, sounds good.
Oh,
Sorry,
wait, sorry. Her laptop is muted. This is why I was trying to avoid doing a just doing a virtual.
yeah, sorry, I thought for some reason I communicated this to you, but it's just
That's
I
okay,
have
Mike.
back to back to back to back things.
I'm just trying to switch you to the other speaker so we can hear you.
Yeah.
Okay. I think you're on the large speaker now, Mike, if you want to.
Okay, I'll give
Test
it
real
a
quick.
shot. Is that better?
Yeah, still not picking up on the, oh, here we go. There it is. Okay, now I think we're good. You
Okay.
there, Mike?
Yep, I'm here.
Okay, let's just turn up the volume on that with the remote. Right?
Oh, there, I can see him. Can you see,
Yeah,
the
that
screen?
looks
You
great.
see-
Yep, looks
you see
great.
the screen share, or can you see the camera as well?
I can see both. The camera doesn't show much except your shirt.
Yeah, it's a
The-
little
the-
close.
the- Okay, now it shows your face. I'm not sure which is better. Let's go back to the shirt view.
My family's on there too.
Oh, are they?
I'm sure my grandma. Okay. Hopefully that's sufficient. Are you gonna put that in the middle of the room? Sure.
Nothing but
Still.
no expense spared here, look.
Yeah.
Ready?
Sure.
You ready, Mike?
Yes, I am ready.
Okay, if I stand here, then
Watch the power cord.
can you point that so I can make sure I can
What do
see
you-
my own ugly face on there,
Oh,
just for a second?
there you go.
Ah, all right, yeah, okay. Stand over here. Okay, thank you very much. Sorry for the short delay there. So we're going to hear Josh Carr give his defence talk. Josh is an MSE student, so he's the first MSE student to go through our group. And he's endured quite a torturous time. A torturous time, but I think one that turned out to be a very productive and torturous time. The torture resulted in some really interesting findings, which I think made his thesis possibly better than we had originally planned. Both chapters were planned and then turned out to be, both experimental results chapters were planned and then turned out to be something different, as you're about to find out. I've just realised I left my notes over there. So he hails from the East Coast, I think in the Virginia area, is that right?
Yeah, Southwest Virginia,
Southwest Virginia,
in the Appalachians.
in the Appalachians, which is what everyone who lives anywhere near the Appalachians says, is that I live near the Appalachians. So
It's not the only defining feature.
his interests are rock climbing.
Yeah, I got some pictures.
Oh, you got some pictures, haven't you? Oh, let's have some pictures. Rock climbing. In fact, he has 3 hobbies that I didn't know about. So I waited 6 years to discover that he likes rock climbing, which will endear him well to at least 2 of his committee members, because they're both rock climbers. Hiking, which brings in the 2 more of the committee members. Golf, which is weird because I had no idea you knew the general golf.
That's a new one.
You hit the ball with. Baking and cooking. I'm not sure where that came from. Necessity, possibly. So with that, I will say that Josh Stark is actually a physicist and then moved into the MSc program. So it's been kind of interesting for us to have someone with a physics undergraduate degree work on our projects. I'm gonna let you go through all these, so you can.
Oh, yeah.
Ease yourself.
Well,
into-
I was trying to get this to work and it wasn't working, but this is my undergrad run of college and also my hometown Salem. And then there's rock climbing and Salida on the top right and golf on the bottom left and rock climbing with my roommates on the bottom right there.
It's nice leg here, George.
Yeah, thank you.
Okay, I'm gonna let you get on so that we
Well,
can get this
So there we
sorted.
go. Now it's working. Perfect. Thanks for the intro, Gary. Well, thank you everyone for coming, the committee and friends and group members. I appreciate you coming to support me and hear what I've done for the last 5 years. So I'm going to be talking about my thesis, which is exploring the limits of Marcus theory to explain charge generation in organic semiconductors. And I'll first start with an introduction to what that means and why it's important, and then pose my hypothesis. I'll follow that up by giving some context of the literature and a motivation for why this work matters. Then I'll describe my experimental methods for how I achieved these results. Then talk about the supporting information for those experiments, and then provide some conclusions and perspective outlook for the field. So to start with the intro motivation, I want to talk a little bit about solar cells. This is solar cell talk, so we should talk at least a little bit starting at solar cells. So on the left here is an inorganic solar cell, which is made of 2 different types of doped silicon, where upon excitation from the sun, some incident rays, you get a splitting of electrons and holes, which then go on to make your current. And these have been really proven to be effective for high efficiency and really long lifetimes. But they're really expensive to fabricate, kind of difficult to fabricate as well. Silicon is metal, so it's pretty difficult to fabricate. And they also lack in terms of their flexibility. They only absorb light at their band gap and can only use the light at their band gap. And so there's some interest in harvesting other parts of the solar spectrum. And that's where organic solar cells come in. But the function of them is a little bit different in that you have, instead of one material, they're made up of 2 materials where under excitation, you have this active layer where you create a bound electron hole pair that then has to be further separated. And so the takeaway from this slide is that organic solar cells can fill that gap that the traditional inorganics cannot. And so let's talk a little bit more about this electron hole pair. What that looks like on a small scale, what the typical device structure of these look like is what's known as a blended bulk heterojunction, where you have this donor and acceptor phase at sort of the very small scale up against each other in these sort of bilayer or blended structures. And you excite the donor, and then you can have the creation of what's known as an exciton or a bound excited state. And that excited state can then do one of 2 things. It can either result in free charges where you get holes on the donor and electrons on the acceptor, which can then go to do your free charge generation. Or you can have an exciton decay back to the ground state. In this case, they're in competition with each other. We want free charges to create our current, and we don't want the exciton to decay. So if we take a closer look at this, we need a donor and an acceptor. And in this work, I've chosen to use 2 different small molecules. One is a donor, a phthalocyanin, and the other is an acceptor, a fullerene. And what this might look like on an energy scale is that you have this bound exciton state here, this electron hole pair that's created in this excited state. And then you have a binding energy of that excited state to overcome to get to your free charges on the other side. And there's this energetic offset, this energetic driving force that gives free energy, delta G. And then eventually, if you can separate that, then you get your free charges in the 2 separate phases. There's 2 problems that are presented in organic solar cells. The first is, well, they both stem from the fact that they're made of low dielectric constant organic molecules. And what does low dielectric mean? Well, it's an electrostatics problem. So if you have a high dielectric environment, something like the silicon, that high dielectric environment creates a much easier pathway for these electrons and holes to separate from each other. It's a lot less work to pull them apart. But in the low dielectric environment, you get a lot less help from the environment that those electrons and holes are separating in, which requires that binding energy to be overcome in order to generate your free charges in organic solar cells. So the first problem is that we have to overcome that extra energy. The second is a kinetics problem. So if we have two pathways, the desired and the undesired pathway, but they're at equal rates, then you only get half of each, which is not very good efficiency. Now, if you double the desired rate and leave the undesired rate the same, you get 67%. But if you go all the way up to 10 times that, you can get up to 90%. And so you need a very, very fast desired rate constant in order to outcompete your undesired pathway, in this case, the exciton decay. So the way that I am approaching this project is that I want to study that fundamental charge separation process to understand those two different rates and try to understand how we can make that charge separation process into the free charges more efficient. So to do this, I've simplified the system by providing a sensitized thin film where we have isolated donor molecules, the phthalocyanin, surrounded by a sea of accepting molecules. And what this does is it allows charge separation to be studied at a very fundamental step where we just have this isolated hole and we can put our free electron into the system and measure the properties of that free electron. And when you do this and measure this as a function of that driving force that I was talking about, we produce a curve that looks a lot like this, where in the red, I have the charge yield, those free electrons being produced as a function of that driving force. And then the photoluminescence quenching of that excited state, how efficiently we separate that excited state in the first place. This is the first study that I'll be talking about. The second study is a system in which we cannot selectively excite that donor, meaning that we're exciting both the host and the donor. And in that case, what we produce is this blue trace here, a much lower suppressed charge yield. And then this red data here is a reproduced data set from the red sensitizer, or the red donor molecules over here, the ones that can be selectively excited. And so the takeaway from this is that Marcus theory is what these plots look a lot like Marcus theory, which I'm going to talk about in just a second. And Marcus theory governs these charge generation processes. And I'm going to explain in this talk why we can make sense of that data from a Marcus theory perspective. So to talk about Marcus theory is a fundamental charge transfer theory, which explains how under excitation of a donor molecule in solution transfers its charge to an acceptor with a surrounding solution environment or a solvent environment. The expression for that is a rate constant K for that charge transfer, and it takes on the form of an exponential Gaussian shape, which looks like this as a function of that driving force delta G that I keep talking about. And there's three important regions to discuss in terms of the shape of this curve. So in the normal region where you have very small driving force, you get a small rate constant because there's this extra energy that you have to overcome before you start to get free charge generation. Then there's an optimal region where you no longer have this small activation barrier, but instead you have just the driving force is exactly equal to what you need to get that rate constant to go. And then finally, we have an inverted region where when you get too much driving force, too much excess energy, you incur this driving force or this activation barrier, which makes your rate constant slow again. And so the key takeaway from this slide is that Marcus theory predicts an optimal driving force to get that fastest rate constant, and that the inverted region here is a very signature feature of the Marcus theory perspective. And to move a little bit further in, this kinetic scheme is the model that I'm going to be working from that takes the Marcus theory approach and extends it to being able to understand from the solution phase to that solid state phase that we're interested in for these organic solar cells. In this case, this is a competition model where we have charge transfer as a competition, and this is called the distributed range electron transfer model, or I'll be calling it DRET for short. And in this model, you have selective excitation of your donor, which can then dissociate into either your free charges or a much loosely bound charge transfer state, which I'll talk about a little bit more in just a second. And this is as a function of separation distance, how we approximate the driving force. And so there's four key features that I'd like to discuss about what this model predicts and uses. So the first is that we use a full Gibbs energy equation, which includes a Born and a work correction, electrostatic work correction, rather than just the difference between the two redox potential levels of our molecules. The second is that we allow a tunneling process of this free charge to tunnel to distances far enough away to become a free charge. The third is that we balance the short range process and the long range process through their reorganization energies in a Marcus-like framework. And the fourth is that we find out that energy transfer is not, it's not always a benefit, but it usually is a benefit for organic solar cells. So the takeaway from this hypothesis here is that we're going to be using a Marcus theory approach with a competition-based model, which allows for very specific predictions to be made about our system, which is agnostic to this short-range charge transfer state directly. And so to end with the introduction, I'll just present my two scientific questions that I'm aiming to answer with this project. And that is that I want to take this solution charge transfer understanding from the fundamental Marcus theory perspective and the solid state charge transfer as it's understood now, and ask the question of what are the limits of Marcus theory to explain the charge, the free charge generation in these systems from the fundamental perspective here. And the second is that if it can, then can we make really nice predictions from that Marcus theory approach to answer questions about the solid state that we haven't been able to before. And so just to summarize before we move on to the next section, for the introduction, organic solar cells can supplement inorganic solar cells, but they lack in efficiency. And the way that organic solar cells work differently is that you have this two-phase system rather than one, where you have a donor and an acceptor blended together into a device, and that has been proven to be the most efficient way to construct them. The second is that Marcus theory makes very specific predictions about charge transfer between molecules as a function of driving force, particularly with an optimal driving force in an inverted region. And then third is that my hypothesis is that I'm going to test that fundamental Marcus theory approach to explain charge separation in the solid state with an attempt to connect the two perspectives together. So I'll now move on to providing some context from the literature and a motivation for this work. So in the literature, it's been observed to see that exciton, that bound state, separate under transient absorption spectroscopy measurements, where they see a near unity charge separated state in those experiments, which has clued people into the fact that we can actually separate that excited state quite efficiently, but that it's the further separation of the electron into the system that's the problem. And in similar fashion, other studies have found that as a function of that driving force that I was talking about from Marcus theory, that they don't see this inverted region at really large driving forces, or if it is, it's a quite weak dependence on that driving force. And these two things in tandem have provided the explanation that that Marcus theory is maybe not very applicable, or that if it is, it doesn't make very good predictions about driving force dependence specifically in these systems. And the model that people have used in the literature for some time is a sequential process where the charge transfer state, this loosely bound charge transfer state after that initial excitation or separation of that exciton, it exists at this localized position at the donor-acceptor interface, where you have a photoexcitation creates that bound excited state. We have this ultra-fast generation of a loosely bound charge transfer state. And then finally, we have that subsequent separation into the free charge state with the relevant rate constants here. And the takeaway from this is that the charge transfer state in the solid state organic semiconductor systems is expected to be a sequential process, that we can generate that charge transfer state efficiently, but that we need to separate it further in order to get our charges in the system. And there's been a lot of studies on the properties of that charge transfer state in the literature. Knowledge of it, because it's the sequential mediator of the process, is that the knowledge of that charge transfer state is quite paramount for understanding the full ramifications of that model system. And so there's been four the way I group them together, four general pursuits of studying that charge transfer state. This top left box here is varying estimations of what that charge transfer state energy is, as it's the energy that people approximate the efficiency of their system on. This is a study from 2020 where they show the differences between varying ways to estimate the charge transfer state and how to model what that looks like. There's been studies on the local electric field, the local electrostatic dependence at that charge separation interface, where they found kind of varying results. In some cases, they find quite a weak dependence, and in others, they find a really strong dependence at that charge separation interface. But as you go further away, it disappears. Further, there's been morphology dependent studies that have showed the importance of delocalization pathways and phases being large enough or long enough to allow that charge to fully separate from its whole pair. And then finally, there's been a lot of temperature dependent studies which have sort of generally found that there's a weak temperature dependence for organic solar cells, meaning that essentially there's not this extra activation barrier that you have to overcome for the charge transfer state. In our group, though, we've observed this Marcus-like behavior quite ubiquitously amongst a varying different number of molecular and polymer systems, as well as large ranges of driving forces. So on the left here is a study from 2012 from our group with a system made up of PCBM and a polyfluorine polymer, where we've seen relative charge yields as a function of driving force appear to be Marcus-like. Similarly, this study from 2020 on a series of tetracenes, paralenes, and rhodonines with pentacene show a substantial Marcus-like behavior. This work from 2016 on carbon nanotubes shows a very similar thing. And then I've also replicated a similar curve in this work that I'll be talking about. And so to summarize this context, the first is that there's this observation of unity efficiency of charge separation, but a lack of that external charge extraction and a lack of the inverted region as predicted by Marcus theory. The second is that the sequential model has this charge transfer state as an intermediate that requires substantial characterization, but can sometimes be difficult to do so. And the third is that prior studies from our group on TRM, using TRMC as a tool, have ubiquitously observed this inverted region behavior. And we think that that begs an answer to understand why we continue to observe that, but the literature seems to not observe that. So I'll now talk about my experimental methods for how I plan to answer those questions. So if I plan to use Marcus theory, it would be apt to use the Marcus equation. So here we have the Marcus equation, and I've changed the subscript to PET now for photoinduced electron transfer rather than just a dark charge transfer from solution as I was talking about previously. I'm going to vary the driving force delta G by choosing a series of different donor molecules. So I have phthalocyanins as well as naphthalocyanins and a few different squarene molecules. I've measured those oxidation potentials of those donor molecules in order to approximate that driving force. Then I pair those with the PCBM accepting host, and I approximate the driving force to the most localized charge transfer state, delta G sub CT, as a difference between the oxidation and reduction potentials of that donor and acceptor and the exciton binding energy using electrochemistry and absorption and emission spectroscopy. So we're going to use the Marcus equation, and I'm going to track two different states. So I'm going to track the reactant, the excited state, that excited donor molecule. I'm going to track the yield of that photoluminescence quenching process, how effectively we quench that excited state using that driving force expression. I've done this with photoluminescence spectroscopy. And then I measure the product of that reaction with the free charges measured by a time resolved microwave conductivity, or TRMC, which I'll talk about a little bit in just a second. And in order to give us the best shot at doing this with a sensitized isolated donor system, I'm spray coating these films to about a micron thick, which is quite thick for thin film measurements, but was necessary to increase our signal to noise ratio to have the best chance of getting good measurements. So let's talk a little bit more about this sensitized process and how we use this in tandem with the microconductivity experiment. So we excite this donor molecule, which eliminates already diffusion because we're exciting one single molecule and it's already beside the charge separation interface with these fluorines. The second is that provides a very well-defined exciton and electrochemical energy from the electrochemistry that I've done. The third is that under charge separation that immobilizes the whole contribution on this donor so that we only have the electron moving. And then we use time resolved microwave conductivity to very selectively and sensitively measure the yield of those free charges And that provides us a very nice way to approximate the absolute free charge yield in this system. And so the key takeaway from this slide is just that sensitized thin film systems provide a very nice solution-like solid state environment to most closely resemble a Marcus theory approach to answer these questions as I've set them out. And so to just summarize again for you for the design, I'm going to vary the driving force with these donor acceptor pairings and approximate that with the Gibbs energy equation. And then I'm going to measure the yields of the photoluminescence quenching and the free charge yield process. And then I'm going to characterize the critical data from those studies. And so to summarize the methods, again for you, donors here, driving force equation, 2 different yield equations, and then TRMC to characterize these thin films. So for the results, this is the curve that I showed at the beginning. This is that free charge yield that I was just talking about, approximated from this Marcus expression as a function of driving force. And the model that we use is this DRET model where we allow a tunneling process. We're also going to, and I'll talk about this in a little bit more in just a second, but just to give you a taste of what I'm going to be talking about, we're also going to be integrating that Marcus expression over that separation distance to sum up the total rate constant for these 2 buckets of these free charges and these charge transfer states at the 2 separate distances. We're then going to assign and fit a reorganization energy to those 2 values or those 2 buckets. And then we're going to also use an included Bohren and work correction, which allows us to add a separation distance dependence to our driving force expression. So on this curve, there's 2 features that I'd like to point out. The first is that we have this Marcus-like trend in the free charge yield with this optimum at about 300 millielectron volts. The second is that the inverted region is present in our system quite substantially at even larger driving forces. And this discrepancy between the blue curve and the red curve is quite disturbing to us. And let me point out precisely why. What this means is that at this driving force of 300 millielectron volts, we're quenching the excited state at approximately 100% efficiency, but we're only recovering 80% of that process as a free charge, which is what we want. So there's 20% that's going to something else. But because we have 100% quenched of that excited state, it's not decaying. There's some other loss process that we haven't accounted for. Furthermore, at the larger driving forces in this inverted region, it's an even worse problem where we have still 100% quenching of that excited state, but only about 10 to 20% of our free charge process at those larger driving forces. And there's really 2 conclusions for this discrepancy. The first would be, well, let's assume that it is that exciton decay process. Exciton decay in these systems is only about a nanosecond or 10 to the 9 inverse seconds. But previous transient absorption measurements, as I stated at the beginning of the methods section, or I'm sorry, the context section, there's been many examples of ultrafast measurements that show that charge separated state happening at about 10 to the 12 inverse seconds or about a picosecond. So I've rejected that as a possibility and instead come away with the conclusion that this loss pathway must be due to that loosely bound charge transfer state that's not able to go on and produce any more free charges in our system. So we amend our yield equations here by including this KCT and KFC separate from this KPET expression, but both of them are going to be understood through a Marcus-like expression. So to talk a little bit more about the separation distance dependence and what this means for these 2 different states that I'm talking about. So I've provided here a cartoon of an individual electron transfer event in sort of a one-dimensional picture where we have the donor over here on the left and just a line of fullerene accepting molecules. And we need to consider some new quantities to properly understand the electron transfer to all of these different fullerene molecules as you go along as a function of that separation distance. The first is that we're going to include a full Gibbs energy expression, which as we prior stated, I had these 3 values, but now I'm going to also include this electrostatic work and this Bohren correction. The second is that I need an approximation for the number of these fullerene molecules. Since we're not doing electron transfer to only 1 anymore, I need to be able to properly incorporate an entropy term for how many of those fullerene molecules we have. We take that as a volumetric sphere to approximate that since we have just an isolated donor surrounded by those fullerene molecules. The third is that we define a radius away from that donor, that we delineate that separation distance to call these fullerenes close by as charge transfer states and these ones further away as free charge states. And then finally, we allow tunneling of that electron from the donor all the way out to those further out fullerene accepting molecules. And we approximate that with a probability distribution, which is just given by an exponential decay with an attenuation coefficient beta. So these are the new quantities on the left that we need to consider. We're then going to take all of these quantities, wrap it up into a really nice expression over here. We're going to approximate these as a Marcus expression in product with our microstates and that probability distribution. And then we're just going to sum up from the donor up to our critical radius, and that's going to be our charge transfer state rate constant total. And then out from the critical radius to infinity or to really long distances, that will be our charge transfer or our free charge rate constant. And then we can calculate the yields using the expressions that I gave earlier. So what this looks like is you get this really nice model to understand that. But furthermore, I plotted these individual rate constants calculated from that approach on the right as a function of driving force. And I think that this allows us to take a closer look at how we actually reproduce this red curve in the data down here. So the DREP model can explain this discrepancy with the understanding that the charge transfer rate constant, KCT, this blue curve, has a really large reorganization energy and continues to increase across this entire range of driving forces. While the free charge rate constant, the red curve, peaks at much smaller driving forces and a smaller reorganization energy across that same range. And so what we end up having is that this competition at low driving force has the charge transfer state rate constant out competing, giving us the loss of free charges here. In this interim optimal region, the free charge rate constant out competes just slightly, giving us the peak in the data. And then finally, way out here, the charge transfer rate constant becomes much, much larger than the free charge rate constant, giving us the inverted region at larger driving forces. And then a final note is just that this black curve is the total rate constant for the photoinduced electron transfer process, which we do calculate to be ultra fast for most of the driving forces from this model approach. And so the takeaway from this is that we have this really delicate fine balance of the two reorganization energies for the charge transfer state and the free charge state, and that gives us that alongside with the entropy expression from the number of microstates gives us this explanation of this loss of our free charges, especially at the optimal and inverted regions. As an extra aside for this study, we did take a couple of extra steps to test what this might look like in a blend case. So on the bottom left here is a cartoon of what this volumetric sphere looks like for our isolated donor case. But we also took a different entropy explanation from a different paper, which approximates the entropy for a bilayer similar to the pictures I've been showing earlier. And it turns out that if you just take that entropy expression and drop it into our DREP model, not changing anything else, you can reproduce a free charge yield curve that has this really broad, flat-topped curve at near 100% free charge separation, and only at really large driving forces do you start to see a turnoff of that. And so what we think is happening here is that the reason that Marcus theory maybe isn't observed, or the inverted region isn't observed in those device studies, is that you would never operate a device at those large driving forces anyway, because your losses would be so large that people are either not observing this or that's why it appears to be weak in those studies. Similar to this study here from a group from 2019. And so to summarize the results from this first study, we have this distributed range electron transfer model that's based on Marcus theory and a competition of those two states. The second is that the DREP model can explain this discrepancy between our excited state species and our free charge yield species as a function of driving force, which a sequential model has some struggle to understand because it would see this photoluminescence quenching and free charge yield curves as being coupled together. And then the third is that the DREP model makes predictions that the number of microstates matters, that entropy and a delocalization through tunneling alongside the Marcus rate constants allow us to explain behavior of both our sensitized system as well as the blend system, our blend device behavior as well. I'm going to take a sip of water real quick. So for the second study, one key feature of the first study was that we were able to selectively excite those donor molecules. So we call these the red absorbing sensitizers because we're exciting them to the red side of the host absorption. So I've shown here this absorption plot. The black trace is the absorption of the PCBM accepting host, and this this green trace is the donor molecule by itself in an inert polystyrene host. And so you can see that it's separated well enough at about 780 nanometers. So we can selectively excite this species without exciting our host. That produces this free charge yield curve that I just showed previously. But for the second study, we decided to look at a subset of molecules that we had attempted to use in the first place, but were not fitting the same, they didn't fit within this paradigm of the selectively excited donors, where instead we have what we were calling the blue absorbing sensitizers, where that absorption was overlapping substantially enough the PCBM accepting host. We could no longer selectively excite it. Instead, we were exciting these at about 680 nanometers. And that was producing a charge yield curve that was suppressed and looked a lot like this. And so we initially had this whole data set, but we plucked out the values of the system where we could selectively excite, analyze that data first, and then we came back to these data points here. And so I'm going to now talk about that subset of data and what we think is happening to those data points. So to take a closer look at this, let's look at a series of these fullerene molecules with this donor and think a little bit about what could be happening for those donors that can't be selectively excited. So first, you excite the donor and you can still have the same charge transfer process to this short range. And in this case, this dashed line is supposed to mimic the critical radius that I was talking about previously. This second process, Roman numeral 2, is to this longer range free charge process. And then third, what we've incurred now with this overlap of the absorption is a possible energy transfer pathway where you can excite the donor and it can transfer its entire excited state energy to a nearby fullerene molecule. And then that fullerene molecule will then turn around and do a back charge transfer to your donor. And so what we think is happening here is that we've constrained this system to only do energy transfer ultra fast and then back charge transfer, and that these two processes have been entirely turned off. Let's move on. We've turned off these two processes, which has led to a much lower suppressed free charge yield. We think that that's happening because when you take a look at a photoluminescence excitation spectrum, in this case, the black trace and the blue trace are for two different films. The black is the neat PCBM and the blue is the blue sensitizer isolated into that system. And when you monitor the emission at the peak of the PCBM emission and march down the excitation wavelength, when you start to excite on this donor molecule and monitor the PCBM emission, you don't get any change in that emission of the PCBM excited state. If we were having some loss of that donor that wasn't doing energy transfer, you might expect that this blue curve might track some of this absorption from the donor and an inert host. But when you monitor a band out at 900 nanometers that we attribute to the charge transfer state emission band, and you do the same experiment, you do see a peak in the blue curve that matches with the neat or the isolated zinc phthalocyanine and polystyrene. And so what we think is happening here is that the excitations that go into the donor are doing this energy transfer and precisely giving you only charge transfer state, which is emitting and giving you this band here, and are not undergoing any decay from the PCBM singlet, that the energy is going into the PCBM and diffusing away. So then where does this free charge yield come from if we think that it's only doing charge transfer state emission? We did an experiment where we directly excited the PCBM host with the sensitizer present. And what happens here is that you have a diffusion process all the way to across a range of separation distances. you can have charge transfer from further away, which gives you your free charges, or you can diffuse all the way to this donor molecules charge separation interface and have your same bound charge transfer state generation. And so what we think is happening here is that there's this competition with this diffusion process, but that some free charges can be generated through this process. However, what we now need to do is incorporate this energy transfer pathway from the donor species as a loss pathway. So if we look back at this picture again, we take out these two and include these as loss pathways. We can now start to fit this model with this included energy transfer pathway as a loss pathway. So previously I had this here, this red curve here is the direct model, assuming that we have 0 for that rate constant. We don't have any energy transfer, as was the case for our previous study. But if you fit that with an energy transfer rate constant here, assuming that it's a very fast, ultra fast, short range energy transfer process at 1 × 10⁻¹2 or 1 picosecond, and fit that to the data using the same parameters, we get a decent fit to the data that properly understands this suppressed yield curve. And then similarly, if we look at this plot again, we can see that the only way that we get free charges is from this competition of the fullerene diffusion to that charge separation interface. And we see that because if we do these experiments and measure the free charge yield, we recover free charge yield from those experiments by exciting directly into the fullerene host. So what this is telling us is that the excitations into the PCB host are the only ones that are generating our free charges in the system, and that the excitations into this donor are not giving us any free charges. And so really the difference between this black and blue curve is the amount that we're exciting the host in each of those experiments. As a final point to bring this back to the blend device realm, what the DRET model might say about this is that the reason that energy transfer is beneficial in those blend systems is because they're designed in a way that can do charge transfer in both directions. So in this case, if we have an excitation into either the acceptor or the donor, where you have large enough phases on both sides, you can do this energy transfer, but then that energy transfer excited state can then still do your electron transfer or hole transfer further away into those domains. But that what DRET would say is that these domains need to be large enough in order to get that process to turn on. And so to summarize the second study, energy transfer in these sensitized films, which can't be selectively excited, robs the sensitizer of any ability to do charge transfer. The second is that in contrast, those excitations into the fullerene host are the only ones that can do free charge generation, but in lower yields due to competing with diffusion. And third is that energy transfer is usually good in blend devices, but both phases need to be large enough and efficient enough to separate those excited states. So to finish, I'll just go through a series of perspectives for the field and conclusions from this work. So the first is that there's an understanding in the literature, especially recently, that there's this idea that barrierless free charge generation is a possibility. But what DRET says is that chasing those barrierless driving forces could be futile, and based on an incorrect assessment of the thermodynamics and the energy of the charge transfer state. Instead, if you use the full Gibbs energy equation to approximate the lowest energy charge transfer state, that is your minimum cost for getting charges in organic semiconductors. The second is that rigid ordered molecules, which have low reorganization energies and strong electronic coupling, are the key to getting free charges in your system, because the two components together allow a reduction of that attenuation of the tunneling process, which allows the electron to tunnel further away much easier. That's consistent with a fast enough approach. The third is that strategies to increase the distance between donors and acceptors with large enough phases to increase delocalization allows for further optimization of this same fast enough approach. And finally is that exciton energy transfer usually enhances the bulk heterojunction device, but two finely mixed domains can still present an asymmetry in charge transfer bidirectionally across that interface. And so instead, ensuring that both phases are appropriately designed with enough entropy delocalization and driving force in both of those phases is enough to do charge transfer. So I'll just acknowledge a few people that have been key to this work. So Gary and Obadiah are co-PI, PI for me. Thank you guys for all of your help. These are the current group members that have been integral to me getting the help that I need, discussions, a lot of good conversation, a lot of good group meetings where I've had a lot of harsh criticism that has made me a better researcher. Previous group members, Taylor and Anya, are both postdocs. Taylor was really crucial early on. He basically taught me how to be a chemist because I didn't have any chemistry. And then collaborators through NREL and CU Boulder, Melissa and Brian are both at NREL and helped a lot with TA and electrochemistry measurements. Seth provided a squaring molecule that was crucial for us getting further into the inverted region in the first study. Mark Spittler provided a squaring molecule for the second study, and Stephen Barlow helped with the discussions from Seth's group. So thank you all. And I'll take some questions for a little bit before they kick everybody out.
Before we get on to the question, actually the way it's going to work is we have questions from the general audience, which is those that do not include committee members. And once we've satisfied ourselves with those general questions, we then ask you to leave the room so that the committee members can then question Josh a bit more deeply, more aggressively, possibly. We'll see. So that's how it's going to work. There's part of this which I always joke that often you fight hard to come up with a new model and then you get to give it a name. And we have two. So we have the direct camp on this side, and I don't like it because it sounds too harsh. It's a very T word. And I thought that would be nice if we had the initials of the four main people that were participants in generating the model, and that's Carr, Allen, Rumbles, and Reed, which unfortunately spells out Carr. And that was one of the reasons we didn't call it the Carr model, because we didn't want to give this guy too much of the recognition. That's a little joke.
Sorry, the ironies of science.
Yeah, that was
Sometimes you just look into it.
Yeah, you could have called it rap, I guess. I think it's back to being inappropriate. So anyway, I will now let the general audience ask any questions if they have any. I know we're a lot of group members here, so but if the group members don't dive in with any questions, we'll just see if there's any others outside the group. Please feel free to fire up anything. You don't have to, if you want to.
Yeah, hopefully I made it concise enough that there's some questions.
We do have one.
You're not on it.
Actually, yeah, I do have a question.
Okay.
How did you choose your dominant subject materials?
Yeah, it's a good question. The acceptor, the fullerene molecule, is picked because there's really two reasons. The first is that it's really widely studied. So there's a lot of understanding of how that model or how that system already works, a fullerene accepting host system already works. The second is that just so happens that we have really good approximations for its electron mobility in the time resolved microwave conductivity experiment. What that means is that when we place the electron and leave the hole confined on the donor, we can also get an absolute yield measurement because we know what the mobility of those electrons are in the fullerene host. So what that means is that it's actually a really crucial point for this study that we haven't had so clearly in previous studies in the group, is that a lot of the previous studies were done with a relative yield because we didn't know what the mobility was. And so we didn't know that there was this possible discrepancy. And it wasn't until we had a host with a really well-defined mobility to get an absolute yield measurement that we saw this discrepancy between the photoluminescence quenching and the free charge yield. And so it's kind of a twofold, really well understood, really well used and easy to use. But second is that it provided that specific control in the time resolved microwave conductivity experiment. For the donors though, it's phthalocyanins, naphthalocyanine squarings are all also really well understood. They're easy to use, they're solution processable, they spray and make films really nicely. They have really high absorption coefficients, which means even when they're isolated at super low concentration, I can still get like 0.5, 0.6 OD of absorption in them in those spray coated films. Just allows for a lot of absorption cross section to get good signals in the experiments. Second is that they also are really tunable for their oxidation potentials. You can put a lot of metals in the center and add a lot of substituent groups to the outside on the periphery that allow them to widely change their oxidation potentials so that I can sweep that whole driving force axis. It's a good question though.
So we'll let the group.
Helena said that she had a question.
Oh,
Oh, yeah, I don't know much about microwave conductivity measurements, and so are those measurements that you have to do in film in solid state form, or can you do those on liquid samples? Like what are kind of the
Yeah, it's a good question. You can do them in solution. That's what Justin does. But that's more aptly called time resolved dielectric loss. And the reason for that is that you also have the solvent environment that you have to worry about, which creates a lot of competing without diving too deep, there's imaginary and real conductivity, and you get a combination of both of those in the solution because of the solvent environment, where you don't have that in the solid state. So the solid state allows for much easier measurement of that real conductivity. But in addition to that, the thin films allow you to place them inside of a really nice resonating cavity, which helps you increase the efficiency further. So
thank you.
yeah, hopefully that answers your question without being too deep.
anybody else have any questions?
Okay, Nick.
Yeah, I'm curious a little bit about if you thought any about what connectivity might look like at other frequencies that would help flesh out the model at all, or have you landed at a frequency which corresponds to kind of the distance that an electron can diffuse if you're curious about electron mobility times electron yield?
So at the gigahertz frequency, you get really nice resolution in the sort of 1 to 10 nanometer range, which is nice for seeing those free charges and seeing them move. You could go up to terahertz. That gets you down to like up to a nanometer essentially, but you probably aren't going to be measuring any more free electrons with a terahertz measurement, at least not very mobile ones. So I don't think that going up in frequency is going to help you measure those free electrons exclusively. Though I don't know about going down in frequency to see if there's a longer range process. I guess it's a pretty good question. Are you asking specifically about measuring the diffusion process exclusive outside of just the yield of the charges?
I guess so you have an idea about what's happening within the time scale of the microwave oscillation. So
Yeah.
probing kind of a specific set of scenarios. I guess at higher frequencies, you have an idea about what the lower limit of your critical radius is.
Yeah,
Might have some other tools to probe.
that's a good point.
Where charge transfer and free charge.
Might delineate.
Yeah.
I think that rather than choosing a different frequency, I think doing something like what Leo does, the optically detected magnetic resonance, is maybe a better tool because you have specific selectivity of those radical species, like the charge transfer state, that are magnetically coupled rather than having both populations.
Yeah. Cool. Nice.
Yeah.
Any more? Okay, well, if I could, you could actually give another round of applause.
So down the hall, kind of an S shape, there's a room 417. There's coffee and juice and snacks and stuff that you guys can eat on and wait while I do this. So you can feel free to go and mingle, but don't feel obligated to stay if you have other things to do. I know it's a Monday morning. Thank you, guys.
I realised a lot of time because camera's pointing at the screen and I didn't get.
Well, it's a wide angle, but yeah,
Yeah.
I did think about that too.
Thank you for using that photograph of the most recent one. I just looked so horrible. Look ill. Sorry, Mike, you have to stay there.
Yeah, because Mike's on here.
You are?
Okay.
Yeah, I probably need to update my photo. I've got more gray hair than that now.
Yeah, that'll be old. Oh, yeah. I tried to not get the black and white Gary photo because you always say that you.
Well, that one's okay. The problem, the new official NREL one just is accurate, and I don't like it.
There's solutions now, Photoshop.
Maybe we
Yeah.
can move the mic a little closer for.
Can you hear us, Mike?
Yeah, fine. I can hear Josh pretty well. The rest of you are, I think, acceptable. I may ask for clarification. if
I'll just
needed.
move the
Um,
closer.
I mean,
Yeah. No, he retired a few years ago, but he's.
How's that, Mike?
Yeah, that's fine. I
He's
think-
now like an adjunct professor at UNC Chapel Hill.
Oh, nice.
And just,
Does he have a research group for it?
no, he just hangs around and works in the
Just
lab.
a smart guy to talk to.
Yeah, he's a smart guy to talk to, but he's one of these people that almost everything he ever says is, we did this back in the 80s.
Right.
We did this back in the 80s. Oh, they don't do it the way we did it back in the 80s. And
Should I put Mike up here?
it's
No.
not.
Huh.
And sometimes
Okay.
that's correct.
Perhaps.
You don't need to hear every third sentence.
Technology has changed a little bit in the last
Yeah,
40
and
years.
to be fair, the two things that he has said is
Maybe I
that
should.
the models was good back in the 80s, and what they lacked then was the techniques and the theory at the level that we have them now. So pulling them out of the drawer and dusting them
Particularly
off.
characterization techniques.
Yes. It's actually more, it's more the quality of the spectroscopy.
That's
To,
where-
to look at the existence of species that back in the 80s just was.
Well, back then it was a whole PhD to build the instrument. Now
Right,
you just order it for a turnkey solution.
yeah, and you have people using Gaussian with reckless abandon, so.
Unfortunately.
Yeah, I always feel sorry when you look in the audience and there's people who in theory, Jerome Cornell was at the meeting earlier this week. He's a really, really good theorist, and Chad Risco was there. And then there's people standing up who do synthesis saying, yeah, we calculated the LUMO and the HOMOs using Gaussian, and they put the full, 631/5G, etc. You can always see the theorist slump. To be fair, they don't use those.
Watch that cord.
Oh, that wasn't productive, was it?
Two women's restrooms and no.
Yeah, it's on the third floor. That was so silly.
Oh, I thought you were gonna get snagged.
Well, yeah, none of the food is ready.
Okay, so
There's no functional elevator, there are no stairways. There's a guarantee. Freaking unbelievable. You can get unbelievable. Someone should be fired. For organizing the building this way. Fired, like, a lot of people should be fired.
Did seem a little silly that they have two bathrooms and it's
Huge
just two women's.
bathrooms,
Yeah.
Like, not like little ones.
Yeah,
like
it's-
massive women's bathroom. A lot.
And even downstairs, there was a women's and a men's. It wasn't even two.
Yeah, I mean, seriously, like, people need to be fired. Like, unbelievable. I'm sorry to have that out there, sir, but.
It's okay.
I snarf, just the bathroom sign has a dragon in a unicorn. It says whatever, just watch it.
It's so large,
I know.
Like, there could be a woman, I mean, if it were like a tiny bathroom, you just like peek in and be like, oh, use it. But there's huge bathrooms.
Yeah.
Huge bathrooms.
all right, well, I think
We should just put up a massive sign that says white men, not longer.
so. We're going to leave the main questioning here, I think, to the two Mikes and Sean, since Obadiah and I have had 6 years of questioning. But
just a quick comment. There are a bunch of other people, Tracy.
Yeah, that's my family. I told them they could leave, but they may not have seen the chat, but family, you can leave. Yeah. How do I boot them?
Because you're the host.
I don't, oh, it's probably over here, actually.
well noticed.
Yeah, maybe I'll just do that.
Well, I'm staring at it, so I don't have a choice.
Yeah, no, okay, there, some of them are leaving. Where's the, oh, they're here, of course. I'll do it this way. Yeah. Remove. Yeah, goodbye. Tracy, oh, report to Zoom, whoops. Did you report, I just reported my uncle to Zoom. Okay. Okay, that's the three of us.
Hopefully you can undo another.
So you're just using Michaela's computer?
Yeah, to control it.
Okay.
That I don't have to, oh, I pulled up a little report box, so I don't have.
You also want to stop the recording so other.
Yes, how do I, that's up here.
Probably on the hosting computer.
This is the host computer. More.
Stop.